Hey, here's yet one more problem where we get to apply the second condition for equilibrium. It says net torque is equal to 0 for an object in rotational equilibrium. The object here is a leaning ladder. So let's draw a picture of a ladder that you might lean against the side of your house if you had to clean your rain gutter or hang Christmas lights or something like that. There we go. Now, in this case, let's imagine a house that has maybe vinyl siding. So most ladders have rubber feet on the bottom. So rubber on grass has a significant non-zero or non-negligible coefficient of friction, but the top of the ladder is just metal. And then, some homes have this vinyl siding on it, and metal on vinyl would give us a coefficient of friction that's pretty much 0, or at least far less than the coefficient of friction at the ground. Okay, so maybe you have some shrubs along the side of the house. So if you're cleaning the rain gutters over on this side, you might be able to lean the ladder at a very large angle, and that would be a lot safer, right? It's less likely to slide out and begin to rotate this way and fall if the angle is steep. But if you have to put the ladder at a less steep angle, then in this case it's more likely to slip and fall. And so the question goes something like this. What's the smallest possible angle? What's the minimum value of theta that you can lean an angle and expect it to still stay upright? So let's say our ladder has a mass of m and a length of L. We've already indicated that the coefficient of friction is practically 0 at this point of contact, but non-zero down at this point. So what are all the forces involved? There's going to be a normal force where the wall pushes straight out on the top of the ladder. So we'll call that N subscript W for the normal force of the wall. Then there's another normal force at the ground pushing straight up. So there's N subscript G. And of course there's the weight of the ladder, and that acts right at the ladder's center of mass. So that's it. Somehow those three forces satisfy these two conditions. The sum of all the forces is equal to 0, and the sum of all torques equals 0. Now wait a minute, how could the sum of all force equal 0? We've got an upward force that could cancel this downward force, but there's a force to the right that hasn't been canceled, so we've obviously left something out, right? There's a force of friction, and it's got to point back to the left, so we'll call that F. In fact, all those forces are easier seen if we just simplify the problem and make a rigid body diagram. So let's draw all those forces in one more time. mg acting at the center of mass. Normal force from the wall. Normal force from the ground. And friction force. Well, the fact that the net force is equal to 0, that can be broken into components. The sum of all forces along the x-axis is 0, and the sum of all forces on the y-axis is 0. So the only way the sum of forces on the x-axis could be 0 is if the magnitude of the normal force of the wall is equal to the magnitude of the friction force. And likewise, the only way sum of all forces on the y-axis could be 0 is if the normal force at the ground is just as large in magnitude as the weight of the ladder. Okay, and then for the net torque to equal 0, well, the only way we can express this mathematically is if we choose an axis of rotation. So some possible choices would be the top of the ladder, the middle, or the bottom. So we can choose option A, B, or C as our axis of rotation. But the truth is, if it's not rotating, if it's at rest, such that omega is 0, then omega equals 0 regardless of which axis you choose. So really any of these would be perfectly fine. The only reason I think C is the best choice of the three is because two of our forces act at that point, and whenever a force is located at the axis of rotation, it's a non-torque producing force. So we're going to choose C as the location of our axis of rotation. So with an axis down at the bottom of the ladder, now we can properly measure our lever arms. If net torque equals 0, then the clockwise torque and the counterclockwise torque have to offset one another. So what tends to rotate clockwise? Well, the normal force at the wall would have a tendency to make this system want to rotate in a clockwise direction about our chosen axis, whereas mg would tend to make it want to rotate counterclockwise about our given axis. So the clockwise torque comes from the normal force of the wall multiplied by a lever arm of, let's see, to get torque we got to multiply force times lever arm. Oh, and this lever arm would just be the full length of the ladder. And then times sine of angle. Well, that's theta, so that's the same theta. Those are alternate interior angles. Oops. Sine theta. Okay, and then our counterclockwise torque is due to the force mg. So torque is force times lever arm. Since it's located at the center of mass, the lever arm for mg is L/2. And then times sine. Now I can't say sine theta because this angle is different than this angle. In fact, this angle here, if we extend the line of the mg vector, it makes a right angle. So this must be 90 minus theta. So there we go. Sine of 90 minus theta. But that's the same thing as cosine theta. Let's go back. Let's see. Normal force of the wall. Let's go back up. The normal force at the wall is equal to the friction force. And friction, well, friction force is less than or equal to mu times normal force. Now what do we mean by that? Remember, there's no friction force up here at the top. So the friction is down here. So we mean mu static times the normal force at the ground. Force of static friction, normal force of the ground. But if it's leaning at the lowest possible angle it could lead without sliding, then the friction has reached its maximum possible value. So maximum force of friction is equal to mu times n. So that's the substitution we can make, right? The normal force is equal to the friction force. The friction force is mu times n, and n at the ground is equal to mg. So I'm going to replace normal force of the wall with mu mg. Mu mgl. I'm also going to divide both sides of the equation by cosine theta. Sine over cosine gives me tangent, and that's equal to mg L/2. So the m cancels out, the g cancels out, L cancels out, and we get mu tangent theta is equal to 1/2, where tangent theta is 1/2 mu. So the minimum possible angle that you could lean the ladder is the inverse tangent of 1/2 mu. So that says as the coefficient of friction increases, the minimum angle decreases, which is exactly what we'd expect.